I don't know how to make this disappear. So
yeah.
sorry about that. Where is it? More.
I'm floating meeting.
Okay. You're expert on that.
So I focus a lot on extreme value theory, and then in my PhD I did a lot of work on completing the asymptotic property of this generalized extreme value distribution. So it's a family of distribution describes the tail behavior of univariate extremes. And then even though this distribution was developed almost a century ago by Fisher and all, but the asymptotic theory wasn't super complete because this family of distribution is sort of complex. And then what makes it tricky was that the support of this distribution depends on the model parameters. And then if you took the asymptotic theory course in your PhD studies, you'll know that asymptotic normality depends on the independence of model parameters from the distribution. So that makes it challenging. And then we developed this existence of unique global MLE for this family of distribution, which seems quite easy for a normal distribution. For example, you can easily prove that the MLEs exist and is unique. And then we also extend that to posterior normality for Bayesian analysis so that we can develop objective priors for this family of distribution. So that's a lot of theoretical development on just univariate extremes. And then I also worked on some spatial extremes, which involves multivariate, right? Many locations. So univariate extreme value theory is already hard, and then extending that to multivariate makes it very challenging because we are trying to study the correlation, the tail dependence between different variables. It makes it like super challenging to study the tail decay and then the interplay between different variables, which I will talk about in this talk, why it's challenging. And then since the theory development is challenging, and then the model is a lot of times very complex, the computational cost for any spatial extremes model is very heavy. And then there's this dire need to apply a spatial extremes model on climate data, but it's still not feasible to apply those techniques on data set with more than like 5,000 stations. So I was able to apply those models on climate data locally, right? I studied precipitation in the Midwest. I studied heat waves in Pacific Northwest, but not on the entire contiguous United States. We would love to study a large spatial domain that has a lot of heterogeneity and also different climate drivers for heavy precipitation, for example. The West Coast, East Coast, and then the Midwest, even Texas, has very different climate drivers for extremes. So when you want to consider a very large spatial domain, then you got to have non-stationarity. You got to have heterogeneous dependence structure for your tail behavior. So today I'm just going to focus on how to build a non-stationary spatial model to model the dependence among climate extremes, right, on a large spatial domain. So a motivation for the development of this work was to emulate complex models, simulation models, such as like those Earth system models that has many components. It couples atmospheric behavior and ocean and all the different components. That's very time-consuming, right? And then it has a lot of PDE, a lot of dynamics in the model. And then what we're trying to do is to build a surrogate model to try to emulate the model output from a climate model, so that we can simulate from the emulator and perform uncertainty quantification and do like a lot of problems that's challenging in the climate modeling, such as calibration, inverse problems, and model choose the correct model parameters for a specific model behavior. And then in the literature, people have dealt with problem to try to emulate how the climate model behaves. The obvious solution is to use Gaussian process to try to emulate that. And then people have also used polynomial chaos expansion. Recently, people started to use deep learning techniques such as generative adversarial networks and variational autoencoders. But they don't consider the tail dependence. And tail dependence is very tricky to capture. It's not just the correlation, right? Correlation, if you think about how it's calculated, is simply taking the entire distribution and then try to evaluate the deviation from the center of the distribution and then try to see how it correlates. But tail dependence is a bit different. We don't care about the bulk. We care about when the extremes happen simultaneously. So it's the upper right tail, the joint behavior for that. So correlation is not a good metric for that. So the purpose of this work is to build a variational autoencoder surrogate model that incorporates a new flexible spatial extremes model that exhibits flexible dependence properties. And then through the efficient implementation of the variational autoencoder, we wish to solve many problems in the climate science challenges. So what is variational autoencoder? I'll first give a brief introduction on that. So we start with autoencoder. Autoencoder is very similar to principal component analysis. What you're basically trying to do is to project your high dimensional data input into a latent space that is much lower dimension. And then using the latent space projection, you can reconstruct the original model output. So PCA is a very good example for that. So you want to try to minimize the loss that the data loss from the encoding. And then you try to also minimize the reconstruction loss when you try to reconstruct the data through the decoder. So autoencoder just replaces all those linear algebra operations for the empirical covariance matrix to neural networks. So it still try to do dimension reduction and then try to reproject. What variational autoencoder does is to project instead of single points, it projects the original output into a series of distributions. And then you can sample in the latent space from those distributions to get variations so that your output will have different behaviors and you will have variations and you get all sorts of behaviors for the output compared to the input. You will not look exactly like the input, and then you bear some resemblance to the input, but also bring variations into the output. So you gotta have to make the distribution that you are projecting onto regularize. And then the way to regularize the encoded space is to maximize this evidence lower bound. So this decoder is essentially a Bayesian hierarchical model. So you have the latent variables that has some sort of distribution. You have the data input that is high dimensional. And then you can think of that as a hierarchical model, right? You have data conditioning on the latent variable, and then the latent variable has some distribution. So that's a hierarchical model. And then what this evidence lower bound is trying to do, when you look at the first term, is basically trying to maximize the likelihood for the data, the marginal likelihood, right? And then the second term is the KL distance between this encoded distribution that you projected onto. We call that variational distribution. And then the true posterior between the true posterior distribution of the latent variable conditioning on the data input. So in some way, this variational distribution is trying to approximate the true posterior, right? So through maximizing the evidence lower bound, you're trying to maximize the likelihood or the evidence of the data, and then also try to minimize the difference between the variational distribution and the true posterior. And then you can do some math, and then you can prove that the evidence lower bound is equivalent to taking the expectation of the joint likelihood and then the variational distribution under the variational distribution. So to approximate that, you use Monte Carlo, right? You simulate from the variational distribution, and then you calculate that term within the expectation many times. And then you can also do a mini batch version of that, because we're basically trying to optimize that elbow, right? And then you can randomly sample the indices and then get a subset of the data, and then try to calculate the elbow just focusing on those data. And then every iteration you select a different batch of the indices. And then the way that we optimize this elbow is through a stochastic gradient descent. So which is commonly used in deep learning techniques. So that's the brief introduction on variational autoencoder. So a very famous application of the variational autoencoder is the deep fake pictures. So you give the variational autoencoder a picture, and then on the top left you have the image input, and then all the other images are the outputs from the variational autoencoder. So what you can see is that it tried to emulate the original output, but the output has some sort of different expressions. Maybe the eyes look sort of slightly different in some pictures. The mouth, the smile looks a bit different, but the general structure is the same as the data input. So what we're trying to do here is to, given a climate model output that has some dependent extremes, we're trying to emulate that map and preserve the dependent structure of the original data input to preserve how extremes happen spatially, right? So that's our goal, is to do something similar with the consideration of extremes. So I've talked about extremal dependence repeatedly. So how do you capture that? How do you measure that? So in spatial extremes, we use this very easy metric called extremal dependence coefficient. So if you look at the form, it's simply a conditional probability. So you have two locations that has weather observations, right? And then what this is trying to measure is to condition on one location exceeding a high level of extremity. So you do have to do some probability integral transformation to transform the weather into the uniform scale. And then you try to see if this location exceeds a very high quantile level, what is the probability of the other station also exceed that high quantile level simultaneously. So this simultaneous occurrence is what we're trying to capture. And then we also want to make a fair comparison, right? So here in College Station, it's still warm, and then it tends to be warmer than Missouri, Columbia, Missouri, for example. So to make that fair comparison, you do have to transform them into their uniform scale. And then you want to capture that simultaneous occurrence so you can capture that at a series of extreme levels. You can vary the U between like 0.9 or 0.9 to 1. And then, so what a good spatial model should capture it should capture many aspects. So I've included four global historical climatology network stations. It's essentially a series of weather stations that keeps monitoring temperature, precipitation, soil moisture, and all that daily, right? And then there are like over 6,000 GCN stations over contiguous United States. I've selected four because they're good to try to illustrate the points I'm trying to make here. I have two stations that are very close to each other. I have two other stations that are far away, and then the distance between Stratford and Bartwell Dam and the distance between Rosser and Kansas City are similar. So they have similar distance. So first, if you focus on the pairwise metric and you want to look at one pair of stations that is further away and one pair of stations that are closer, you can imagine that at the same level extremity, closer stations should be more dependent. So that means when you have a storm happening, Bartwell Dam and Rosser should have higher probability of experiencing the same weather extremes than Bartwell Dam and Stratford, right? So that is intuitive. And then the second one says that you focus on two locations, but you let the extremity increase, then the dependent strength should also decay. So that's just trying to describe the localization of storms, right? The thunderstorms, for example, when you have very heavy precipitation, like 100-year return level extreme precipitation, it tends to be localized. And then when you gradually increase the extremity level, this dependent strength should decay. So that is the weakening dependence for the dependence measure. And then the third one is the non-stationarity, right? So even though Stratford and Bartwell Dam and Rosser and Kansas City have similar distance, the dependence metric between those two pairs of stations should be different, right? It shouldn't be the same just because they have the same distance. If your spatial model is stationary and isotropic, then your pairwise dependence measure will be the same just because they have the same distance. But it shouldn't be true, right? When you consider a large spatial domain like this, even just locally in the central United States. And then the last one is kind of hard to capture in spatial extremes, which is what we call the spatial scale aware dependent structure. So which is to say that for two stations that are really far away, like San Francisco and Boston, they should really have very little extremal dependence. The climate drivers for those two locations are vastly different. So you got to have a model that ensures you have long range asymptotic independence and short range. In the short range, like locally, you also have to have the model flexible enough to be able to capture both asymptotic independence and dependence. So what is asymptotic independence? Asymptotic independence happens when you let this metric, let the U converge to 1 and see what this metric happens. So if this metric converges to 0, you have asymptotic independence. If this metric converges to a positive number that is non-trivial, that is greater than 0, you have asymptotic dependence. So that's how you define those. In the existing spatial models are limited because we're talking about the extremal dependence here. The most commonly used Gaussian process will be too weak in their tail dependence because, like as you know, Gaussian tail is very light. So no matter how, yes.
So don't I get the difference between the fourth property and the first property, the last slide.
Yeah.
This one, so the first one and the first property.
So you're asking about this property and the second one?
And the fourth.
the fourth. So they're not mutually exclusive. So they are talking about the same thing. The fourth one is more focused on the limit, how the limit behaves differently, whether it converges to zero or it stays at a positive level.
Okay,
Yeah. Great question. So, which is shown in this plot, right? If you examine the tail, the pairwise tail dependence for a Gaussian process, no matter how close the two sides are, the correlation function usually gives you higher correlation when the distance is low, right? So no matter how large your correlation is, as long as it's less than 1, the dependence metric chi will behave like this. You will plunge down to 0. So that means there's no dependence in the tail for Gaussian process. It'll be too weak to capture the tail dependence. It's the same for the inverted max stable process. So for multivariate extreme value, people have come up with max stable, which can capture asymptotic dependence. But what problem does it have? As you can see in this plot, as long as you reach a certain level of extremity, for example, in this case, as long as you reach 0.9 or 90th percentile, your dependence strength will become constant because it has max stability. So that is also not realistic, right? As we talked about, we want the storm to localize as you focus on higher and higher extremity level. But this one is constant. So that means your storm size will be the same, no matter whether it's a 50-year return level or like a 100-year return level. If you use max stable, the storm size will not shrink. So that is not physically realistic. So both of these models are not good. It's too rigid. We need a model that can capture both dependence behaviors and have it weakening as your quantile level converge to 1, right? But it's very hard to find a model that has such properties. What curve do I want?
Like in Florida.
Can I draw it? Sure. So let's say I want to look at distance equal to 1. It may be dependent, right? Because they're close to each other. So I may want the curve to slowly decay. But the limit, the absolute limit at the 100th percentile, it should converge to some positive limit, but it's still decaying, right? So this cannot be captured by max stable. What if I increase the distance to 10? Then I want this dependence to be consistently lower than this chi measure. I want it to converge faster, maybe down to 0. So I want a variety of dependence behaviors. If I let the distance go to like 0.0001, then it should behave more like a max stable. So I want this variety of behaviors. I want to be able to capture both asymptotic independence and weakening dependence and max stable dependence. So you want the model to be able to capture that. But if you use Gaussian, what will happen? There will be converging down to 0 for all 3 of them. For max stable, there will still be constant. So that's what I'm trying to capture in the tail behavior. So one successful implementation of the model that can exhibit this large class of dependence behavior is this what we call the max infinitely divisible model, max ID or max ID. So what it does is to do a scale mixture. So you have this YS, that is a spectral or basis representation. So you take some basis function, and then you mix that with a series of independent heavy-tailed positive stable distribution. And then you mix them together to get a spatial field. And then you add that with noise. So what this what's essential is that these parameters should be heavy-tailed. So you can imagine if you're using the radial basis function, radial basis function has a center, right? So that basically allows you to model the extreme behavior locally, and then the center of the radial basis function can be considered as the center of the storms, and then you radius out, right? And then the heavier tailed Z is, or the higher value Z is, that means locally you have stronger storm, and then you radius out. So this is the model, which is sort of simple. And then so the heavy tail distribution that they use is the positive stable. So positive stable distribution does not have an analytical PDF, but you can get the Laplace transform very easily. It has a clean form. But we want to add an additional parameter such that we can control the tail decay even more. So we want to use the exponentially tilted positive stable distribution. So basically, in this case, you have this additional theta parameter. This theta parameter so both alpha and theta controls the tail decay. But when theta is positive, then your tail decays slower. So you get weaker storm to be able to get weaker storm. So consequently, this model can capture both asymptotic independence and dependence, depending on the value of theta, depending on how much you tilt the tail decay of the latent Z variables. But the drawback is that it doesn't solve the last challenge, which is the long-range asymptotic independence and short-range asymptotic independence or dependence. Why is that? Once you fix the value of theta, then your model is either asymptotic independent or asymptotic dependent. It's not spatially variant. As you fix the theta value, then the model has to be asymptotically independent when theta is greater than 0. That means no matter how close your two sides are, there's no dependence in the limit. Or the other way around, when theta is actually equal to 0. So that's not realistic, right? As we talked about, San Francisco and Boston should really have the independence in the tail. So so that's one drawback. Only one dependence class. Long-range asymptotic dependence and short-range asymptotic dependence cannot be satisfied at the same time. And there are many other issues with this model. So we still find this model very useful. So what we're trying to do is to change out this model. We, instead of using a radial basis function that is not compactly supported, meaning that it has non-zero value over the entire spatial domain, we control the effect of the center of the storms. So we pre-specify a series of knots and have the center of the storm radius out, but we don't let it impact the entire spatial domain. So we control the impact of the storm, and then we also let the theta parameter, which controls the intensity of the storm, to vary across knots. And then we also let this alpha parameter. So alpha parameter basically let you control the tail decay also in comparison to theta. And then we separate it out from the white noise. So the previous model, the alpha parameter for the white noise and for the latent basis representation is the same. So we separated them out so that we decouple the marginal behavior and the tail dependence. So through the spatially varying theta parameter, we can get spatially varying dependent structure. The intensity of the storm is different at depending on where you go. And then also the long-range asymptotic independence is automatically ensured because of that compactly supported basis function. San Francisco and Boston will not share basis functions. So the one storm cannot impact San Francisco and Boston simultaneously. So you have that long-range asymptotic independence assured. And then what's nice about this model is that the positive stable distribution will guarantee that your marginal tail behaves like a Pareto anywhere you go. So that's very useful to evaluate that kind of measure, which I introduced, the pairwise tail dependence measure. And then with this nice property, we can derive the dependence property. So the theory looks quite dense, but I'll just illustrate using the two plots here. So let's say you have a spatial domain that is square, and then you have 6 knots, 6 storm centers. And then the effects of each storm center only radiates out to a certain spatial extent. So the red color are theta equal to 0, meaning that they are very dependent. The intensity is very high. But the blue colors are theta greater than 0. That means weaker storm. So let's say I pick Si and Sj. Since they're not covered by strong storm, they will exhibit asymptotic independence. What if one location is covered by strong storm and the other station is not? You still have asymptotic independence. When do you get dependence then? The dependence happens when you have the 2 locations both covered by the same storm. So in this case, Si and Sj is both covered by this basis function. But what if Si, instead of being in the intersection of these 2 storm centers, what if Si is here? Then they don't share the same storm. They will become asymptotically independent. So the dependence only happens when you have strong storm, and you have to be covered by the same storm to be asymptotically dependent. So this is one of the few models that can capture this variety of dependence in the literature. You can do asymptotic independence and dependence at the same time. And then the transition will happen smoothly through the control of the phi parameter, which is another dependence parameter that I didn't go into detail about. So how do we embed it in the variational encoder? As I introduced, the decoder of a variational encoder is essentially a Bayesian hierarchical model. And then we did do dimension reduction, right? We try to represent the spatial process using a very small number of knots and radial basis functions. So that is essentially dimension reduction. So we place the positive stable variables in the latent space, and then we utilize the hierarchical construct of the max ID model for the decoder, and then the elbow can be expressed, right, through some specification of the variational distribution. So through the optimization of the elbow, you will run a variational distribution that is as close as possible to the true posterior from the latent variable to the data input. So this is the overall structure. We have the input, and then we feed it into multi-layer perceptron neural networks, and then we impose the ReLU activation function at each layer, and then the decoder just takes the random sample from the latent space, and then we can do it repeatedly to get many replicates of the original data input. And then this is the form, which is less important. This is just gives you an idea how the model parameters are specified and also how they are optimized. So I'll quickly go through some simulations. So yes.
So like with the symptotic dependence,
Mhm.
depending on the, I think, the parameter tau, right?
Mhm.
Like with respect to the Colloquium models.
Right. Yeah.
So when you actually have a stronger storm, I understand that you're actually providing the symptotic dependence.
Mhm.
But even if the storm is not that strong, if it's sharing the same,
Mhm.
then wouldn't that comply as symptotic dependence, but with a lower value of tau, but still?
Great question. Yes. So when I was saying about strong storms, I use the same shaded color, but the strength can be different.
Yeah.
So you can capture weaker, still kind of strong storm. It can still be asymptotically dependent. So what we're trying to capture is that at different distance, even though they're covered by the same storm, larger distance will have weaker dependence, which means that closer to station may have a limit that is greater than faraway stations, even though they're covered by the same knot. So, yeah, great question. So, and if you look at the form of the chi measure, it is dependent on the weight, right? So you can imagine closer stations will share higher value of weight. And then also it's controlled by many other components of the model. So it's really controlled by many aspects. It's not just covered by the same basis function or not. So great question, great. Okay, so our simulation involves a square spatial domain. And then we randomly simulate 2,000 sites and fix it. And then we simulate from the max ID model for 100 replicates for 2,000 sites. So this is a astronomical spatial dimension for spatial extremes. And then our parameter settings are like that. And then we use 25 knots. And then the spatial extent of the storm centers is around 2.5. And then the theta parameters, which controls the dependence class, are specified as follows. So you have 3 zeros, which gives you the options of asymptotic dependence. All the other storms are weaker than those 3. And then here is a temporal, here is a time replicate, one of them. It looks like that. And then we simulate 100 output like that, and then we try to emulate those 100 spatial output, and then try to learn the spatial dependent structure, and then to give you emulations that has the same properties as the data input. And then here's how we decide whether you converge or not, which is an important issue in stochastic gradient descent. So we basically try to like at that through a moving window of 1,000 iterations, we try to compare the algo value of the current 1,000 iteration to the previous 1,000 iteration, and then try to plot out this difference plot, which is in red. So the light blue is the algo value itself, and then as long as the difference plunge down to a certain like low threshold, we decide convergence. And it's very fast, very efficient for 2,000 locations.
Convergence threshold, square or
something. So it's the moving average of the algo value, and then we try to compare that to the previous window, so that it's not just the current iteration and the previous iteration. Because of the stochastic gradient descent, it's not monotone. Even though it's trying to optimize the algo, it's not monotonically increasing. It has some variations as you go. So you have to do some sort of average from a number of iterations. So here's a comparison. So on the left, you have the simulated data input. In the center is what we emulated. And on the right, we use the heterogeneous Gaussian process to try to emulate that. So as we talked about, Gaussian tail is very light. and then it can get the overall structure correctly, but it cannot give you like a very large spatial extent for the extremes. And then here are the QQ plots. So this is not a very good diagnostic. What we did was simply put all the observations on the left into a vector, and then compare it to the same the other vector from the emulated map, and then try to compare the quantiles to see whether we got the data range right. And then here in the center, you have the comparison between our emulator and the Gaussian on the right. So the Gaussian tail is very light. It's not able to capture the tail, the heavy value of the data input. And then here is a empirical estimation of the chi measure. So what I do when I empirically estimate them is as follows. So you have 2,000 locations, right, randomly in the space. Let's say I want to estimate the distance at 0.5. So what I do is to grab all the pairs that have approximately the same distance with some tolerance, right? So I grab all those pairs, and then I have replicas of the pairwise behavior, and then I empirically estimate the chi measure, which is a conditional probability from 0 to 1, a grade of values from 0 to 1, and then I get an uncertainty bound from these many estimates. And as you can imagine, when you gradually increase the quantile level, you have less data. You're focusing on higher and higher extreme level. So your uncertainty will increase as you increase the quantile level. But the overall structure is that it started out as completely dependent when you have when you focus on the 0 quantile. And then it starts to decay. And then it has this behavior where it's weakening. And then in this case, we do have asymptotic dependence locally in 3 regions. So in this case, the limit is non-zero. And then I compare that from the empirical estimate from the emulation and the truth. It matches up really well from 0 to 1. So this is a surprise, yes.
So value of U quite matter in this analysis, in my understanding. How do you choose this U?
So we're not choosing U, we're estimating it from 0 to 1. So it's the entire data range from 0 to 1. So in spatial extremes literature, you will notice that people usually start from 0.9 to 1 because they try to focus on the tail behavior. But what's surprising in this case is that we even captured the bulk of the distribution really well. The bulk of the distribution means that the low quantile from 0 to maybe like the 3rd quartile, 75%. So this is another, I'd say, surprising accomplishment of this model is that you can capture both heavy tail behavior and the bulk behavior. So this encouraged us to look at the parameters estimates from the decoder. So since this is a variational base estimation, we can draw from the encoder repeatedly and then have different variable estimation. And then, so I did that for 1,000 times very efficiently. From each draw of the encoder, I get a parameter estimate, and then I get a point cloud of the parameter estimates. So depending on how accepting you are to variational base estimation, so I say this this can be an approximation of the posterior distribution of the parameters conditioning on data input. But some people think that that's debatable because variational base, when you try to decrease the KL distance between the variational distribution and the true posterior, you're not doing it 100%. So it's not exactly the posterior distribution, but what we can see is that the point cloud covers the true value. And even for zero value, so we do have 3 knots that have 0 values that gives you strong storm. And it still captures it really well, even though it's on the boundary of the parameter space. Usually when you have a model that has parameter value at the boundary of the parameter space, it's hard to do uncertainty quantification. But in this case, since we use the ReLU activation function, it will automatically give you a lot of zeros. So the true value is well captured even when the two true thetas are both zeros. So it's still trying to push it to the corner for the point cloud. So I have, I think, 5 minutes. Here are the credible intervals for each parameter. We have 25 knots, so we have 25 credible intervals, and then as I said, we do want to specify the knots. So in a lot of cases, we don't know where the knots are, and then we develop an algorithm to try to use the data to inform where you should place the knot instead of specifying a uniform grid, right? So we also compare the performance between the true knots and then the data informed knots, and then the performance is still really well. And then we also compare the CRPS and MSP. So as we also try to simulate data from other models, right? As we've seen, it can somehow capture the bulk of the data really well. What if we simulate from Gaussian process, which is not heavy-tailed? As you can see, you can even capture Gaussian process, even though it's not developed for a Gaussian process. The reason that it works is because you can let the theta value to vary. When theta value is very large, then the tail decay behaves like a Gaussian distribution. So as long as you pick the right theta value locally, then you get the right behavior. And then apply this on the data set that has more than 16,000 locations. So this is the first time that a spatial extremes model can be applied to such high spatial dimensions, and then without doing the local analysis. A lot of people separate out dissects the spatial domain into many subsections, and then they try to estimate them locally. But we don't do that here. We just entirely look at the spatial behavior. And then here are the spatially varying theta values. We can average over time, or we can average over space to look at the spatial variation and then the temporal variation. So an amazing feature here is that we see that on average, the theta value increase over time. So there's a gradual shift in the dependent structure. So we were able to both capture the spatial non-stationarity and the temporal non-stationarity using the variational autoencoder. And then this is also the first time that people considered the spatial variation, the temporal variation in the dependent structure. So for free.
Question.
Uh-huh.
Looking at the monthly max temperature, right?
Right.
Monthly min.
Uh-huh.
Did you look at the monthly min?
The monthly min? No.
From a practical point, from an interpretation point of view, more interested in the monthly max. And see more of it.
So if you do monthly mean, you can just use a Gaussian process to do that because it's not heavy-tailed. So we want to have a process that has large values. So when you do monthly maxima, you're basically putting the high temperature event, many high temperature event that happen throughout the months, and then impose it on the same map. So you get larger spatial extent. So we can, in theory, apply this to monthly mean, but we're really trying to get a data set that has large spatial extent with dependence. And the reason why people don't consider temporal variation in spatial extremes is that they either take block maxima or they do peaks over threshold. And they just assume temporal independence. So, which is another reason why this is important, because it's giving you options to study the continuous variation of the spatial extremes. So I think I'll do it 1 more minute. So a natural extension of the current work is to do conditional variation autoencoder. So you tell the autoencoder what condition you want to simulate from. So one example for this is that, what if I want the subject to wear glasses? What if I want to change the hair color of the subject? Then you can tell it to do it differently. So convert that to our climate application. What if I tell you that this climate output is derived from El Nino or La Nina? So the conditions can be different, and then you get different dependent structures. You can tell the variation autoencoder to do things differently. So that's one application. And then the other application is to try to get dynamics into the model. I had a very intriguing conversation with Brani just before this talk. He suggested to use wavelets in spatial extremes. And I think that's a great idea, is to try to build some dynamics into the model so that it's more realistic, so that you can capture the daily variation, not just the monthly maxima. One extension that we're trying to look at is Chris Weikel's very early work on stochastic integral difference equation models, or IDE models. So what that is to try to study the diffusive or propagation dynamics in the model through this translation kernel. So you can treat that as how the storm moves, right? So at time t, you have a spatial map. How does it evolve into the next time? It's through this transitional kernel, and then you add the noise to that. A realization from that map is that you started out with a storm that looks like this, and then it gradually moves, right? Because that's how the translation kernel is trying to control that. So what we're trying to do is to incorporate that in the max ID model, so that we can gradually look at how the extreme weather behaves for that. And we're still at the initial stage of working on this problem, and this is the summary. And yeah, our manuscript is archived. So thank you very much.
Any other questions? I think then let's start our speaker. We do not have seminar next week. Instead, we have the bioinformatics symposium. So we will resume our seminar series looking at. All right, see you guys 3 weeks ago.